In this two-part presentation, we'll be exploring the universe with SOFIA. Thanks for joining us. My name is Michael Shinneberry, and I am with the museum's education department. The universe is a very, very colorful place. It's even more colorful when you look at what you can't see. And that's what we're going to do with SOFIA. SOFIA stands for Stratospheric Observatory for Infrared Astronomy, SOFIA. It is a German-American program that carries an 8-foot telescope into the stratosphere so it can see the universe in light that does not reach the ground. In September 2015, I was privileged to fly on 2 SOFIA missions, along with Jeff Killebrew, science teacher at the New Mexico School for the Blind and Visually Impaired here in Alamogordo, New Mexico. The SOFIA program pairs educators from a community to learn and then teach by doing. One is a formal teacher, and here that is Jeff, with an informal educator, myself. Jeff holds 2 patents for devices that assist sight-impaired students in learning mathematics, and he has been honored numerous times with prestigious national awards. We'll be taking you along on the SOFIA mission a bit later in this presentation. But first, what is the stratosphere and why take a telescope up there? We live in the troposphere, the lowest part of the atmosphere where weather takes place. Just above is the stratosphere, which means layered. Next comes the mesosphere, or middle atmosphere, and then space. How high is the stratosphere? Well, that depends. At Earth's equator, the stratosphere begins 12 miles above the surface. At the North and South poles, the layer starts about 6 miles high. Most important to this story, the stratosphere is stable and very dry. The light that lets you see this video is just a tiny slice of the electromagnetic spectrum, which is pure energy. X-rays used by doctors and dentists and ultraviolet light that causes skin cancer are high-energy forms of electromagnetic radiation. Our eyes work in a narrow mid-range that the atmosphere passes. Low-energy radiation includes heat that you can feel from a fireplace, and radio waves like Wi-Fi and satellite TV transmissions. This chart shows the span of radiation for the most part we humans encounter every day, whether we know it or not. If you set this spectrum across the entire United States, with the low energy or radio waves at the west coast and the high energy or gamma rays at the east coast, the visible spectrum would only be about the width of a dime. Infrared instruments measure heat radiation, like me glowing in these 2 photographs at the Sunspot Solar Observatory in New Mexico. At left, notice the 2 lights in the upper right. You'll see that those register in infrared as very hot. My left shoulder is reflecting infrared, as are my glasses. The color image is called false color infrared, where colors we see are assigned to different heat levels from the infrared image. Water droplets in Earth's lower atmosphere absorb infrared light. Thus, most of the infrared spectrum rarely makes it to any Earth-bound telescopes. In addition, infrared telescopes need to be refrigerated so their own body heat does not shine brighter than the objects that they study. So, while we orbited a range of gamma-ray, X-ray, ultraviolet, and visible telescopes, infrared needs time to catch up. So why look at the invisible? A great example in the night sky is the constellation Orion. To the ancient Greeks, Orion was a mighty hunter. Here in southeast New Mexico, Orion is one of the largest and most visible constellations in the winter night sky. The first image shows Orion as seen with the naked eye. The 3 angled stars in the center make up Orion's belt. Perhaps you remember the reference from the original Men in Black movie. Follow the line down from the left of the 3 stars and you see the Orion Nebula. You really don't see much there except a couple of stars, do you? Note the large star in the upper left. That is Betelgeuse, commonly mispronounced Beetlejuice after the film of the same name. Betelgeuse is the 10th brightest star in the night sky, and in artwork is in Orion's right armpit. In fact, in Arabic, Betelgeuse means the armpit of Orion. Although only about 8.5 million years old, the star is dying and has expanded into a red supergiant. Now we see Orion in infrared. Notice how much hotter the images are in the Orion Nebula? This is a very active area where new stars are being birthed. Also, notice how insignificant Betelgeuse is in infrared. Because it is a dying star, it's colder than the nebula and isn't really very impressive in this photograph. Now imagine how much more of the universe is hidden in invisible radiation. The first infrared telescope in space was the Infrared Astronomical Satellite, IRAS, a joint American-British-Dutch project launched in 1983. In 10 months, it opened a new window on the universe as it discovered 350,000 new objects, mapped the core of our galaxy, and found hints of planets around other stars. This led to a series of orbiting infrared telescopes, including the Herschel Space Observatory and Spitzer Space Telescope, and infrared cameras aboard Hubble Space Telescope. But space is expensive. So astronomers also took an intermediate step: telescopes on jets. In the 1960s, NASA flew small infrared telescopes aboard a Learjet and a Convair 990. From 1974 through 1999, NASA operated the Kuiper Airborne Observatory with a 3-foot infrared telescope. Airborne telescopes can only observe a few hours at a time, and part of the infrared spectrum is still blocked, but they are less expensive to operate and can be repaired or fitted with new cameras as technology evolves. And as usually happens in astronomy and science, discoveries lead to more questions requiring bigger telescopes and better cameras. Meet SOFIA, the Stratospheric Observatory for Infrared Astronomy. The German Aerospace Center developed an 8-foot infrared telescope, and NASA adapted a retired Boeing 747 SP jetliner to produce the largest airborne observatory ever flown. For comparison, SOFIA's main mirror is the same size as Hubble Space Telescope's mirror. SOFIA's pictures are blurry because sharpness drops as wavelength increases, but they are still sharper than anything we've had before in infrared. Thanks for watching Part 1 of Exploring the Universe with SOFIA. In Part 2, Jeff Killebrew and I take you and a special guest into the stratosphere aboard SOFIA.